Again, it's a pleasure being here today, and I'm giving this talk with my IEEE hat, and trying to see. Right. I'd like to cover broadly telepresence as a field. And in particular, I like to focus on how can we increase the autonomy and the intelligence of machines that are observing the human actions during the telepresence, teleoperation, and learning from those examples. And overall, to discuss the impact on our society from these new technologies. The concept and the terminology of telepresence has slightly changed over the years, and now, according to Wikipedia, it refers to the broad set of technologies that allows a person to feel as if they were present, and to give the appearance of being present, and or to have the effect, for example, via telerobotics, at another place than their true location. I marked into this diagram, and I'm going to show this diagram again, this schematic, with A being the operator or the customer in a specific application, and with A prime the avatar or the robot at the remote location, and with Z another user at the remote location, and with O the environment. And you can see on the left side an operator with some form of an interface by which it controls the avatar at the right, and it can act on the environment as if it was he or she was in the remote environment, and the person there in that environment feels that she interacts directly with A as if A was in that remote environment. So we would call A prime an avatar of A. More so than in conventional teleoperation, telepresence emphasizes the human experience at both ends. So one controlling the avatar remotely and the other one interacting with the avatar. The main functions in interacting during telepresence relate to the sense, decide, act, or perceive, decide, act kind of chain. And in particular, if we refer only now to the remote robot, it needs to sense the environment in which it operates. It needs to communicate this data back to the remote user, and a decision needs to be made what to do next, and then an action is performed on the environment. Decision itself, decision making, can be local if we are talking about an autonomous machine, or remote if the machine is teleoperated. And it can be slide in between, it can be shared between the remote and the local environment. The user, and again, user A, the customer in a specific application, gives goals or instructions or commands to the agent, and the agent, again, acts based on those instructions. Acts upon the environment, and through the sensors, again, determines the status of the environment and acts upon it and communicates the data back to the remote, to the user. In the case of a robotic, space robotics platform, as it's illustrated on the right, the case of Mars rovers, we have the data that's sent back is, for example, both engineering data, which relates to the status of the rover, the position of the rover, the position of the different instruments, and the status of different instruments, the battery levels, and so on, as well as the science data, basically what's obtained from different cameras, instruments, and other systems on the rover itself. You see an illustration of a diversity of instruments that is on the illustrated as if for the Curiosity rover. And you see also how the communication back in the case of space robotics takes place. In general, the rover communicating with an orbiter, and then the orbiter communicating via the deep space network to the mission operations. So there is a channel of communication between the user and the remote robot, and usually there is a delay associated to this communication, which if you're talking about the moon, there may be second level delay. If you're talking about Mars, is maybe on average 20 minutes delay, which makes it more or less impossible to have a control, which a joysticking type of a control of the remote platform. Why do we use remotely operated machines? In some cases, the environment is beyond human capabilities, and Mars is such an example. It takes about 6 months with the current technology to get humans to Mars, and it's a flight in which you are under radiation and different other stresses. Although the environment is just purely deadly, like was it the case of the Fukushima nuclear plant, which was affected by the tsunami and the earthquake, and basically people had to go inside and expose themselves to radiation. So in cases where it's high risk for health or life, and the pandemic significantly impacted us in every aspect that relates to collocation, and the direct access to the labs, for example, and of course to seeing other people in general being collocated has been affected. So there is a need to bring the expertise where it is needed, when it's needed. And in the case of the COVID, it meant that there were more patients than doctors, and there was a need to also share the doctor's expertise rapidly among patients. There's a time and cost to access. Also to try to keep the personnel, the doctors, the nurses, and so on, to keep them safe from others who are infected. So in general, we're talking about the better quality of life, and there are some trade-offs here, but safer from the risk of infection and less time on the way to access the location of work and so on. It does have economic advantages in several situations by increasing the productivity and reducing cost. So there is a history associated with telepresence, and artists imagine how it would look over 100 years ago. You see on the left the video telephony with a projection device that shows the lady and the interaction with these microphones. In the middle, you see how the doctor of the future examines the patients. That's from 1925, and you see the doctor looking into this magic mirror on the wall and seeing the patient at the other end, and using this mechanism to interact with, basically to do the remote consultation of the patient. And on the right, you see this is in 1965, the space telerobotics vision with a humanoid robot with a TV camera head that, and the wording say remotely controlled robot-like teleoperated TV camera heads are technically feasible and could be of great value in unmanned space exploration. So It does have the origins in access to dangerous environments. It started as Telerobotics, started in the nuclear industry in the 40s, and the manipulation of nuclear and chemical materials. Also, very early for undersea operations, and it's used for exploration, for waste management, pollution monitoring, and so on. And as I mentioned, in outer space for exploration, sample acquisition, and deployment or repair for space systems. Important moments include the introduction of supervisory control by Thomas Sheridan at MIT in '74. But the actual founding of the field, it's considered 1980 for telepresence, and by Marvin Minsky, also at MIT. And it's important to quote this statement from Minsky at that time, saying telepresence is not science fiction. We could have a remote control economy by the 21st century if we start planning right now. So the emphasis here is on the word economy, the remote control economy. So which includes a variety of services in healthcare, in education, and work in the field, and so on. And also in 1980, visiting at MIT was Professor Sumutachi from University of Tokyo, and he uses the word teleexistence with almost the same meaning as the latest version of telepresence. And his vision for avatars, which are basically the remote agents, was presented at the X Prize Visionary Summits in 2016, and it led to the Avatar X Prize competition, a $10 million competition, with the idea that such avatars would permit anyone to log into those avatars from all around the world anytime, and to interact anywhere. So the most common aspect of telepresence is the video conferencing. At some point, actually, telepresence became almost synonymous with video conferencing, and Cisco systems are among the best into this. And you have people sharing let's say a discussion room with many of them being presented on the screens. But it's also used for control of vehicles and drones. And the picture on the middle top shows a pilot of a drone which sees on various screens and has joysticks and instruments to control the plane. Remote surgery, again, an ability to see on screen the specific area that's been operated, and to interact with special type of devices that provide also haptic feedback, force feedback, and so on. Lower left, you see the use for remote control of construction machine, and you see also the use in space science missions. You see a scientist trying to explore a specific rock on Mars and pointing to the rover as if he or she would be on the surface of the planet. And then you have the idea of a virtual hospital, virtual care center, in which doctors would be accessing and interacting with a variety of patients, and that's deployed at least in the prototype stage in a variety of hospitals. I mentioned also the Susumu Tachi's lab in University of Tokyo, and a lot of focus also on virtual reality, which it's going hand in hand with telerobotics, but in this case, obviously, the interaction, the remote location is a virtual location, it's a simulated location. And again, the ensemble of both real and virtual is this teleexistence. So In the traditional sense, telepresence refers to a real environment, but again, the boundaries have been blurred in recent time. But clearly, in teleexistence, it refers to an action in a remote environment, which is either real or virtual. We see a variety of funding agencies now that are investing explicitly, again, in the word telepresence, in studies that involve telepresence and research involving telepresence. This on the right is from the European Commission, it relates to extended collaborative telepresence. On the lower side, I'm illustrating this with the Avatar X Prize that I mentioned. You see on the right the number of applications that would be enabled by telepresence for work on Earth, for also in space, Moon and Mars, and in outer space in general. So what is in the teleoperated platform on this avatar? So on the lower part of the screen, I'm illustrating a couple of things. The operator, you see it with the red circles, that's head-mounted display. So it's looking through the screen. It has some kind of an instrument, a joystick or a mouse of some sort. Their remote location, you have this robot that potentially has a display or some other way to represent, to give the appearance of the human at the remote location, arms and cameras, including eye in the hand, for example, camera, and a variety of end effectors, and a mobility system. So in this particular case, a wheeled one, but also legged have been proposed. So basically a bipedal or other forms of robots. On the right, you see a couple of modalities of interacting. Some people are using just simply mouse or joysticks or the control platforms for games, the control interfaces that are used in games. And you see on the screen on the top right a scene where the robot interacts with a person at the remote location and does a couple of actions, including some actions that is doing jointly with the remote person. But not only an anthropomorphic robot with arms and head and so on, but a camera for all practical, a car for all practical purposes, a vehicle. It can be a teleoperated avatar for the purpose of this discussion. There are a couple of important interrelated fields that I'm not going to talk too much about that, but in general, the embodied machines, so robotics, autonomous vehicles, and so on. The virtual worlds, starting with virtual reality, augmented reality, things that happen in games, digital twins, the interfaces, including wearables, the infrastructure, sensors and actuators and decision making could be in the smarts of the infrastructure itself, in smart cities and transportation infrastructure and so on. Communications, internet, wireless, internet of things, and so on and so forth. And there are aspects related to the ethics of telepresence, privacy, safety, in general, things related to operating near humans. And I'm not going to touch much on them, but I'll start with talking about a couple of key technology areas. The first ones are the ones located at the machine end, and then I'm going to talk about ones at the human end, and then about how the appearance is generated at the remote location. In all of the above, artificial intelligence has a role, or can have a role, from the design of such systems to the real-time understanding and decisions related to the system. If we think of machine sensing and then perception after communication, we can address a variety of sensors like sensing and perception modalities, including vision. So basically the sense of sight and hearing, and those are the most advanced. The dominant perception is vision, and in general relies on CMOS sensors or arrays, and mainly RGB, but also infrared and so on, and also potentially doing 3D mapping with light or acoustic sensors. Haptics is important for specific applications, as I mentioned in robotic surgery, for example, and it may not be that important for other applications, for example, like driving a remote vehicle. And of course, we have resolution, baseline, size of the array, a variety of characteristics for each of these sensors. In general, sensor processing happens on the autonomous system itself on board, but in some situations, the processing happens at the destination, and for that reason, it needs to be compressed. And that introduces sometimes bottlenecks and also trade-offs, and it can be lossless or lossy compression, more and more lossless compression being used, and that trade-offs depending on the sensory map, cost, size, volume, mass, and so on. In terms of the comparison between machine perception and human perception, let's just give the point of the human vision, and at 120-degree field of view, we have approximately 500 megapixels, and by comparison, in an iPhone, we have about 12 megapixels, and in the displays, for example, we have about 16K resolution and 130 megapixels and so on. Audio, it's in general satisfactory, but a lot of other improvements are still needed in terms of producing the exact feeling that you have when you are in the remote location. The other are quite still in need of development. The tactile, olfactory, gustatory, all pretty poor. Although the virtual gloves and so on have seen some progress in recent years. I mentioned the delays in communication. There are, especially when you're manipulating something at a distance, you need to receive the feedback from that environment within less than 200 milliseconds in order to feel normal. If there is a larger delay, there is basically a confusing situation, and you can't really operate correctly, and it can lead to instability, especially in the case of force feedback. And the solution for that are, for example, slowing down the action, or a move and wait strategy. So wait until the remote operator has caught up and then perform the new action, or modeling the delays and doing some prediction and operating with the predicted response, which you'll see through a simulation, or give a higher level commands, and which is to some extent an equivalent of a move and wait for the action to be performed autonomously at the remote location. If we do a comparison again of the effect of this delay and bandwidth on a specific perception, images on a 4K ultra high definition have about 8 million pixels and 33 million pixels for 8K. And the transmission on Netflix, for example, is 25 megabits per second for 4K. And the delays could be order of seconds due to compression. So to achieve the equivalent of the human vision at 500 megapixels, 20 frames per second, 24 frames per second, one needs of the order of 12,000 megabits per second. So this is even beyond 5G if we want to achieve that. As a reminder, the 5G speeds would go up to 1 gigabit per second and we need about 10 in order to see this real-time full vision feedback if we operate with the with communication constraints. If you are in a remote platform, let's say so-called self-driving car, there are different levels of autonomy, and by the way, the levels of autonomy themselves were also introduced by Thomas Sheridan, I mentioned, and at the lowest level is when the computer offers no assistance, so the human must take all the decisions and actions, and slowly an increasing role of the computer to offer a set of decisions or narrow down decision to a few or just only one alternative and so on. And basically at the highest level of autonomy, the computer decides everything and acts autonomously without any intervention from the human. And in terms of levels of automation, basically no automation when you drive the car manually, and the full automation or level 5 of automation when the vehicle performs all the driving tasks. And it's a debate in the industry whether it's useful to have this shared control, because one claim is if the human is not involved in the action and suddenly needs to be to intervene again in a difficult situation, there is a reaction time, and the human has lost, let's say, the ability to be in the loop. Correct. So that's why some people talk about having directly full autonomy and not going through the levels of autonomy in a progressive way. For a passenger in the car, it actually is the same whether the car drives autonomously or there is a remote driver that controls the car through the internet. And that's illustrated on the left, and a couple of companies are following this particular platform, for example, so the human driver takes over the control remotely. And the infrastructure, the transportation infrastructure and so on has a part of it also in determining, again, position, the car doing optimization of the route and so on. Since I mentioned autonomy, there is here a couple of categories in which autonomy is partitioned, and the things that relate to the situation and self-awareness. And here is where you have the perception, the state estimation, knowledge and model building, hazard assessments, and so on. Then the reasoning and acting, which includes planning at the higher level, mission level, then activity level, and then motion planning, execution and control, and so on. And then different aspects related to collaboration, interaction, and engineering and integrity, VNV, test and evaluation, modeling and simulation, and so on. Again, this is a diagram for orientation only, and it's has some changes, but in general, this situation awareness and the reasoning and acting and so on are continuously used. So where is the intelligence? Is it remote or is it local? In the first example there, you have the teleoperation, and in that case, you have either a human operator or you have a computer that controls over the, let's say, over the internet, or anyway, through some interface. Or you on onboard autonomy, the human is only for the role of an observer, perhaps, or giving very high level command, and the intelligence is on board the computer. But it's interesting that if we do teleoperation in the beginning, the intelligence is at the operator, but after illustrating and going through the motions of teleoperation, the intelligence can be transferred to a computer, either somewhere in the cloud or on board. So that's kind of how this I'm illustrating this transfer of intelligence. In terms of how do we actuate, well, we need wheels, legs, and so on, manipulation with arms and hands and fingers. The size, again, it's dependent of the application, but convenient to humans if they interact with the humans. And especially the interaction of humans, you need to have safety to address safety issues, and it needs to be comfortable and pleasant for the humans to interact with. The perception, again, it's facilitated through interfaces like displays and head-mounted displays and so on, and headsets, and also virtual gloves and joysticks and different modalities for obtaining the input from the force or the pressure at the remote location. I'm including here under decision aids, but the various aspects of simulation and in general the intelligent assistance, and you have interaction in natural language, and you could have basically recommendations and decision-making aids, and an important role is played by the virtual reality or different forms of extended reality, which includes the augmented reality, where you overlay digital information on real world elements, or a mixed reality. In terms of the command interfaces, I mentioned the joysticks and the keyboard. You could type, you could use voice, you could use gestures. And I'm illustrating on the lower side some of the interfaces, for example, developed in our section at JPL with this so-called bias sleeve that collects EMG sensors, collects EMG signals, and converts it through machine learning to the specific language of command that's transmitted to the remote robot. In terms of appearance generation, well, some people go to the length of making the robot looking very much like the human, and they deal with this geminoids, for example, or the face of a human is displayed on the robot tablet or screen. And there are also a variety of virtual displays and projections of some sort, and including holographic projections. The most common ones is the one in the middle with robots with a face display on a screen, which is rather primitive. It obviously doesn't give you the full feeling that the person is at that location, but it offers still a modality of interacting with capturing expressions and things that would be otherwise lost if you don't have the visual interaction. So teleoperation itself, as I mentioned, provides examples for learning, and in the initial guidance of the robot basically shows how to solve a specific problem. And through these training examples, the machine can learn, and thus the intelligence of the system can be increased. The earliest example that I'm aware of this is the learning to drive by watching. This was done at Carnegie Mellon in the early 90s, and this was the work of Dean Pomerleau and the entire team that worked with NavLab. So on the left side in particular, we see the neural network, or an article related to Alvin, which was the autonomous land vehicle in the neural network, which was a free layer network backpropagation designed for road following. And it drove actually in 95, it drove across the country autonomously, 2,800 miles out of 2,850 miles was autonomously on 55 to 60 miles per hour. And the part on the left, it says, interactively training the network on real road images taken as the human drives the MATLAB, develop a system that adapts and to the circumstances, in contrast to the other autonomous navigation systems, which rely to fixed structure, inflexible algorithms, and so on. So the lower right, it basically illustrates the mapping that's happening between the image seen of the road curving and the action on the wheel, and basically turning sharp left or sharp right and so on, depending on the curvature. And this mapping is basically the what's the neural network learns, or the system learns from the training examples provided by the human, more or less teleoperating the vehicle. By the way, in many situations, it operated in simulations such that it can learn from how to handle accidents or situations that you wouldn't want to train during on a real road. So basically providing examples of unusual, let's say, situations. I applied actually this same idea from NavLab with this time with manipulators. So my PhD was actually on motion learning by imitation for humanoid robots. This was the earliest thesis on robot apprentice learning. And the mapping, as opposed to being off the road to the commands of the steering wheel, it was a mapping between the image of the arm and the control to the joints. It was basically through watching the human move the arm. It was a learning of the model that provided the eye-arm coordination. I think I need to move a bit faster. So it's important to into all this interaction, as the more we increase the autonomy to understand what other actors in the scene are doing. For that one, the sensors, as I mentioned, they can be in the robot itself, but they also can be in the walls or in general in the cyber-physical infrastructure. When we look at a particular person, we're trying to understand who the person is, what is the intent of that person, to try to predict, for example, the movement of the person, and what the person commands, or what the person does as an action or interacts with other users. So some of them are dealt by biometrics, like who is the person. Some are more the medical condition, what is his mental state or health, what is he doing as an activity, what are the commands, and so on. And for understanding people's activities, a variety of tools are available, but for example, the process algebra, which is good for analysis, and LTS, good for visualization and matching, can lead to these sequences of primitive actions. Not only to recognize a specific activity, but also to predict what activity is taking place. It's essential for a robot that would operate in a human context. Now, what's the impact on society? We refer to telecare, to teleeducation, and telework. The telecare is important because we have order of 40 million Americans living alone, and there is a loneliness, and there is a need to care about them if they are affected by different illnesses. But there are also challenges related to that in terms of the human safety from the robot, manipulation challenges if you need to carry or to lift the person, to apply force on the person, and so on. Telehealth is being seen, especially during the pandemic now, and you can have a consultation online with which is covered by most health insurances. There are some robotic nurses deployed in hospitals, and an established practice of telesurgery. Da Vinci systems are among the most well-known, but there are limitations, in particularly in if you want to attach to a remote person that doesn't have already the devices, and moving the devices, the sensing devices or the instruments on the person. In education, there is an impact. Obviously, the education can be done through teleconference, teleseminars, and so on. But the bottleneck usually is being in the labs. How do you run a remote engineering lab? And the simplest way, of course, is if you have network instruments. But there may be, providing cameras to see what's going on in the lab is important to see, for example, things that are not captured by instruments, like an object under the experiment changing shape or color, or how it interacts, two objects are interacting with each other. But a missing link into that is the mobile manipulation. For example, taking a prototype from the printer, assembling two subsystems, connecting a new instrument, and so on. In telework, it's important to operate the equipment as if you were present in the cabin or control room. As a matter of fact, you could do even better than that, because you would have, through the displays, more information that you would get if you were in the cockpit, let's say. But again, interfaces are important in order to allow optimal command. And I'm just showing here also the lower images in the minority report, where you just basically you have a very rich display and very human-oriented modality for interaction. If you use telepresence for transportation of goods, you could have a remotely controlled vehicles, and there is experiments on all of those. In particular, the lower slide illustrates the on the left, the driverless truck convoys. So you drive basically, let's say, the first vehicle, and the other ones are more or less following the tracking in a column. And also there are already companies that are providing, for example, in San Francisco, food delivery. You see the lower right, and those are teleoperated through the streets, because again, we don't have yet the full autonomy that would be needed. This lack of an autonomy on robots actually made me to use human avatars. So I had about a decade ago, I had a startup that operated in 18 cities in Europe. It was called Telemediators, for telepresence mediators, and you could do a variety of you could provide a variety of services could be provided. The most important one was the telepresence tourists. So you have these avatars that you'd control over tourist attractions in European capitals. But also we did the first avatar or telepresence mediated shopping, where basically the customer indicated the product to be purchased, and the telemediator made a payment and shipped it, and so on. There is a recording of this presentation at Caltech in 2010 on YouTube. Also, we did the first basically simultaneous telepresence of two different avatars at two different locations, which in principle could do work. So it allows a way of multiplying my capability, or a person's capability, to perform work at multiple locations at the same time. But there are a couple of lessons learned through this experience with this company. One of them was that clearly, at least even in the public places, it infringes on privacy of people. It may generate different reactions, and in some situations, actually, it may break the law. In UK, there was this law that you couldn't kind of film or show videos of children into this public events and so on. So obviously it attracts a safety, security risk. There is a psychological impact potentially coming from telepresence. Again, loneliness has been something that affected many people during this separation from other people and so on. And in general, telepresence helped, to stay in contact with our families and friends. But if we are moving totally to telepresence, there is this risk of loss of social gratification and so on. So in the end, it might actually increase the loneliness. In terms of the physical fitness, again, there is a chance that through not staying too much on the computer, there is a decrease in the physical fitness. Although, in principle, if you have extra time, you could use it to exercise instead of being in the car in a fixed position during the telecommuting. You could use the time in a different way. I mentioned already the privacy, safety, security aspects. This is even what we get from our phones and through the devices. Already a lot of things. You can have GPS give you the position where you are, and of course the habits from shopping and so on. But the privacy and security risk related to household robots relate again to interconnecting with other robots in the homes, data collection, physical interaction, and risk of infecting, having hacking, and so on. But in general, the economic impact is the fact that we can empower more people. It's no longer a must that we are collocated to the place of performance, and that has an impact on many aspects of transportation, urbanist pollution, and so on. And we do empower the people to do more. Each individual can supervise more jobs. Again, you need autonomy at the end, because the robot needs to do the action in between the commands, but you could have one single individual do multiple pieces of work at different locations and can do more sophisticated work aided by the intelligence of the machine. So you could have actually a 24/7 economy. The impact on housing is just illustrated in here. Right now, if you want to buy a small apartment in Pasadena, it's $800,000. If you go 34 miles away, you buy double the size, and you're living in a nice environment in nature, as opposed to living in a crowded, urban agglomerated neighborhood. The people decide how to live based, again, quality of healthcare, quality of education, commute, job availability, but all of those are changed totally through telepresence, or can be changed totally through telepresence. So if all this would be telesified, you could have the education online and no need to commute and so on. That will have an impact clearly on where we live. Market. The predictions for telerobotics, teleoperations market is in the order of close to 100 billion in the next 6-7 years. Some 76 billion by 2026, 98 billion 27, and so on. Out of which there is close to $1 billion market by 27-28 through the telepresence robots themselves. Again, the global teleoperations market includes other aspects, not only this small robots that we are presenting. So we could have this telepresence economy. We could have a system level optimization and adaptation and evolution through the intelligence of the machines involved, and in general, a seamless integration of the human cognition in this cyber-physical infrastructure. And we're hoping for an optimized and personalized life in which health and happiness are part of what we are. So as a summary, telepresence frees us from physical presence limitation. It allows the transfer of the human intelligence to the machine through the training, let's say, that is done through learning by demonstration. Learning by observation, let's say, and teaching by demonstration. It's a multiplier of human intervention and eventually of AI intervention, and has a revolutionary impact on the workforce, on conditions of work and lifestyle. It's more than outsourcing. It's basically outsourcing in real time for everything that was not outsourceable, but it's also insourcing, since it brings opportunity to us from wherever we are. We could work at a distance. Finally, I just want to introduce this pilot project on telepresence, part of the IEEE Future Directions, and we had a workshop which it's available on IEEE TV, which featured both Thomas Sheridan and Susumu Tachi, who were co-chairs but also gave the keynotes. And I would welcome your involvement in this Telepresence project, and please let me know by email if you would like to join this initiative. Thank you very much.